In this video lesson, we're going to be covering content in Chapter 2, Section 1, the derivative and the tangent line. So here are a couple of note cards that I extracted from the content. So our objectives are to find the slope of the tangent line to a curve at a point, use the limit definition to find the derivative of a function, and describe the relationship between differentiability and continuity. So going back to the second bullet here, use the limit definition to find the derivative of a function. So we're going to just add a little note over here. So kind of an informal definition of a derivative is that a derivative is an equation for the given function that gives the slope of that function at any x. All right, to help us with our understanding of the definition of a derivative, we need to look at slopes of secant and tangent lines. So this first part right here deals with information about what is a secant line. Well, a secant line to a non-linear graph, that just means that we're dealing with a graph that's not linear. We could, but typically we deal with non-linear graphs. So what is a secant line? Well, it's a line through 2 points on that graph. So over here in our illustration, I can see part of a function. I can see 2 points here. Okay? If we connect those, then the line between those 2 points on this chosen function is called a secant line. So the slope of that line, that secant line, is also referred to as a secant slope. Okay? Additionally, that slope is also referred to as the average rate of change, or simply AROC, from x sub 1 to x sub 2. So if I labeled x sub 1 and x sub 2, since this is my first point, I might call that x subscript 1. Since this is my second chosen point on that function, if I drop it down to the x-axis, I can call that x subscript 2. So this is point 1, this is point 2. Okay, typically we can label them x sub 1, y sub 1. We can label this x value x sub 2, and then y sub 2. And more about this notation on the next page. Okay, so average rate of change from x sub 1 to x sub 2, also known as the secant slope, the slope of the secant line. So this m just represents slope. So m secant, the slope of a secant line. Well, the slope between 2 points is y2 minus y1, difference of the y's, over the difference of the x's, x2 minus x1. All right, so in our example up here, let's go ahead and put in the notation that we have for those two ordered pairs. So our y2 would be considered the functional value, or the y value, at the point c plus delta x. So that all represents y sub 2 minus y sub 1. We'll find y sub 1, that's f evaluated at some c, that's the y value. The difference of the x's in our 2 points in the way we labeled them, x sub 2 would be c plus delta x minus x sub 1, which is just c. And of course, these will cancel. So rewriting that, keeping the same numerator, and then just recording the delta x in the denominator. So this expression would give us the slope of the secant line through these 2 points on this curve. Okay, more about the c and the delta x. As you can see from this point right here, we've labeled it some x value called c. The y value, if we knew what the function was, we could put the c value into the function to get the y value. So we call this ordered pair c comma f of c. Now, if we want to consider this second nearby point right here, I'm moving horizontally some delta x, some change in x. So that's where the delta x comes from. So if this is x sub 1, I move over some delta x. So in this case, it's called C. You increase your x value by delta x to line up vertically underneath this second point. So that's where this order or this coordinate came from. We started at C, but we increased horizontally by some change in x called delta x. So that means that this y coordinate right here could be found by plugging in whatever this x is right here, if I knew what it was, by plugging that x into the function if I knew what the equation for the function was. It gets a little tedious, I guess, with this notation. It looks a little bit confusing, but if we just think of these as x and y coordinates, especially the y coordinates in function notation, hopefully it won't seem so strange. All right, so this represents the slope of a secant line right here. We need 2 points, we subtract the y's, we subtract the x's. Mainly what we're concerned about in this lesson is the slope of what we call a tangent line. So what is a tangent line to a nonlinear graph? How is a tangent line different than, say, this secant line? Well, remember, a secant line goes through 2 points. A tangent line to a nonlinear graph is a line at 1 point. And so we've got some illustrations over here. All right, consider this function. It looks like a downward opening parabola. Let's say we're interested in this point P that's on this function. If I were to draw a tangent line at P through F, this function F, that tangent line would be something like this. It'd be horizontal. We know the slope of that is 0, and that's going to be something we're going to look at a little bit later, but that is a tangent line. So a tangent line at 1 point. So let's look at the second case right here, another example of a tangent line. So we've got a different kind of function, y equals f of x. We've chosen this point right here. What does the tangent line, if drawn to the graph at point P, look like? Well, this particular tangent line actually is kind of interesting because part of the tangent line is above the curve and the other part of the tangent line down here is below the curve. That's a special point that we're going to study in a later section, but this is still an illustration of a tangent line. All right, and then looking over here at our third illustration of a tangent line, we've got a different curve, y equals f of x. We've chosen this point P to be our point of tangency. We draw in a tangent line to the curve at that point. That line intersects the curve in 1 point. Okay, and some might say, well, what happens down here as you get further away from this point P of tangency? Notice that the tangent line intersects the curve again, whereas we thought it was supposed to just intersect at 1 point. Well, the thinking is this: I just want to intersect the curve at 1 point in a local area. I don't care about what happens further away on that tangent line, but if we just kind of focus in on right here, doesn't matter what happens with that tangent line and that curve if they intersect again. This is kind of called local linearity. All right, so this would be a representation of that tangent line. All right, so back over here, a tangent line is described to be the intersection of a graph at 1 point. We also call that instantaneous rate of change, or IROC for short, also known as tangent slope. So this tangent line, its slope is sometimes called the tangent slope. We call it the instantaneous rate of change. This line just represents the slope of the graph at that particular point P. So let's come back over here like we did to find the slope of the secant line. How do we find the slope of a tangent line when all we're given is 1 point? In our previous work, all we've ever done to find slope is use 2 points. So how can we find the slope of a tangent line if we only have 1 point? And that's really the point of this whole lesson, is how do we find the slope of that tangent line with just 1 point? All right, so we're going to do some investigation down here. All right, let's consider the function f of x equals x squared plus 1. Of course, you can put that in your calculator and graph it. I'm just going to record a real quick graph of that upward opening parabola over here. All right, f of x equals x squared plus 1. You would graph it. It's a parabola that opens up. Okay, this ordered pair is 0, 1. So it asks us to sketch a graph of f. I did it. Draw a tangent line to this function f at x equals 2. Well, I'm just going to kind of eyeball it and say, okay, if this is x equals 1 and this is x equals 2, I'm going to go up to the graph. Okay, and right here is my point, having x coordinate 2. Now, if I wanted to find the y coordinate when x is 2, I would just plug 2 back into the function, 2f of 2, and I would know exactly what that y coordinate is. Well, I'll just kind of real quickly by inspection, if x is 2 and I square it, I'd add 1, I'm going to get 5. So we can call this point 2 comma f of 2. That's a representation of the y coordinate, or specifically we know that value would be 5. And just for the sake of this lesson, I know this isn't really drawn to scale, because if that y coordinate is 1, how can that be 5? Well, I needed to make this graph a little bit wide so for what I'm doing. So just kind of ignore the fact that it's not really to scale. All right, so we sketched a graph. We drew a tangent line, or no, we have not done that yet. Now let's draw the tangent line at x equals 2. So we come in here, we find x equals 2, we find this point, and I'm trying to draw in a line that just touches that point at 2, 5. Okay, and kind of snuggles up against that graph right there. Okay, and remember, later on this tangent line, I may intersect the graph in another place, but all I want is one point of intersection with the graph right here in this small little area. So this would be my tangent line to the graph. Okay, and down here, okay, if you look, it says the tangent line, what I have drawn, and the graph become indistinguishable as you zoom in. Meaning if you were to graph the equation of this tangent line and the function and just keep zooming in, you wouldn't be able to tell the closer you got in what was the tangent line and what was the function. And that's important to us because I know how to handle a line. I know the slope of a line. Okay? I can get the slope of the line, and what happens is the slope of that line is the same as the slope of the graph of the function at that point of tangency. Okay, that's a lot, but we can always, rewind the video and listen to that again. All right, so I drew a tangent line to the function at x equals 2. Now it says, given the slope of the graph at x equals 2 is 4. So now this is just given to us. Later we're going to find 4, but right now, okay, we're just told that the slope of the graph at x equals 2 is 4. Okay, so that means the slope of this line is also 4, because the slope of a tangent line is the same as the slope of the graph at that x value of point of tangency. So this line has a slope of 4 and the graph has a slope of 4. All right, so given the slope of the graph at x equals 2 is 4, the slope is 4. Okay, well, in our studies of using equations of lines, whether it's slope-intercept, like what was on that index card, or whether we're using point-slope, which was on that index card, typically we use the lowercase letter m to represent the slope. So I'm just decoding. Given the slope of the graph of this function at x equals 2 is 4. That means m is 4. Write an equation of the tangent line. When we read write an equation of the tangent line, okay, we think either slope-intercept or point-slope, both of which were on the note cards. Well, here it says use point-slope. That's pretty common for us to use point-slope in calculus, as opposed to the other version, slope-intercept. Okay, so let's write an equation of this tangent line. Okay, well, in that equation, we need x sub 1, y sub 1, and we need slope. And we actually have those things. If you come back over here and look at this point, 2 is our x sub 1, and 5 is our x sub 2. And then m is 4 because it was given to us. So I'm going to come over here. So in our equation for this tangent line, we keep y, we keep x. We insert the values for y sub 1, m, and x sub 1. So this becomes y minus 5. I went up here and grabbed the 5. 4 gets put in for m. Quantity, x minus 2 for the x coordinate of the point of tangency. This is fine. This is a safe stop. This is point-slope form. If you want to put it in slope-intercept form, then we would have to distribute the 4 and then add the 5 to the other side. Unless you need to do so for Webb assign, there's no reason to put this equation in slope-intercept form, we've accomplished the task of writing an equation of a tangent line. So if you wanted to get a visual of what you found, then you might want to solve for y by adding the 5 so that you can put this in the calculator. And so if I added the 5, there would be no reason to distribute the 4. If I wanted to get a visual of what I've recorded here, okay, I could go to y1, insert the function into y1, and in y2, insert the equation, the equation of the line, graph them both at the same time, and we should see this kind of illustration pop up on our graphing calculator. All right, so in summary, the tangent line and the graph of f become indistinguishable as you zoom in. And you can practice that if you type these into your calculator. Right, the slope of the tangent line to the graph of f at the point c comma f of c is also called the slope of the graph of f at x equals c. So the slope of the graph is the same as the slope that's on the tangent line. And oftentimes we're interested in rates of change on specific functions. And so if I wanted to know what is the rate of change right up here, well, the graph is increasing more rapidly. Chances are the rate of change, the IROC, instantaneous rate of change right here, is going to be greater than 4. A visual of what that might look like, try and draw in the tangent line at this point right here. Maybe it's the point x equals 5. I don't know. But if you try and draw in the tangent line at this point on the function, notice that this line, okay, is more steep than the green line. Now that's because the graph is rising more rapidly. Okay, so what if I wanted to find the slope at any point on this function? You know, I need a way to do that, and that's what this lesson is about. Likewise, what if I wanted to find the slope of the graph over here somewhere at this x value? Well, I can see the functions coming down. If I were to try and sketch in a tangent line visually, it might look something like this. I know the slope of that line is negative because that line's going down. So somehow in my work that I'm about to learn, okay, I should be able to get a negative value out for that slope. So this line has a negative slope, and that's because the slope of this graph, okay, is also going to be negative. Okay. All right, so continuing looking at slopes. All right, this says approximate the tangent slope using a secant line through the point of tangency and a second point on the curve. So again, our main problem is how do we find the slope of a line when I only have one point? Well, what we're actually going to do is we're going to create 2 points and then use our study with limits that we were working with earlier, okay, to help us find the slope of a tangent line. All right, so these are just illustrations here. It looks like right here, we will, in all these illustrations right here, we'll just kind of look at this one. We've got a function. Okay, so we're interested in this point called c comma f of c. I don't know what c is, it's a value. And if I knew what that x value was, I'd plug it into the function and get the y value. Okay, so in these other 3 illustrations here, I can see c f of c, c f of c, c f of c. And what's changing as I kind of work my way down is I have some horizontal distance between this point, this other chosen point here. I'm just picking it out of the blue. I have some horizontal distance between this other chosen point and the point that I'm interested in, this point called CF of C. Well, as we work our way down, notice what's happening. We're actually taking this other point and we're moving it so that it gets closer and closer and closer to the point CF of C. So you can see down here that delta x, this horizontal distance, gets less because the horizontal distance between these 2 points is decreasing. Well, notice that this point is even closer now to CF of C, so delta x is actually going very, very small. So at some point, okay, that point that we're going to move is going to be either right next to that point or possibly even on top of that point, which means that delta x value, that horizontal distance, is approaching 0. And we've kind of seen this notation in our work with limits before. So what happens here is that this secant line between 2 points, as I move this point closer, okay, to this point that I'm interested in finding the slope of at that point, this point is getting closer and closer to it, to the point where I'm like, okay, I think this secant line is becoming that tangent line. Kind of a similar illustration here, but just kind of notice the change is that the point that we're interested in right here is CF of C. So this point stays right here, but what changes is we're moving this darker point down closer and closer and closer to CF of C, which same thing, the horizontal distance between these 2 points is getting closer and closer, and it's also approaching 0. So the idea of finding the slope of a tangent line really comes from finding the slope of a secant line, but then setting up a limit problem where that distance between, horizontal distance between those 2 points approaches 0. Okay. So just looking at maybe labeling this point right here to help us understand these 2 formulas down here. So this point right here is called CF of C. So if I move over horizontally some delta x amount off of C, I can call this x coordinate C, whatever it was here, maybe it was 2, increased by, maybe I'm increasing it by 1. So I would call it 2, or C, increased by the delta x amount, maybe that's 1. So that would be the label for this x coordinate. Well, how would I get this y coordinate? Well, I would have to plug in the x coordinate to the function to get the y value. So if I wanted to label this point right here, I could call it c plus delta x, comma, the function evaluated at c plus delta x. I could call all these points the same. Well, I don't have one here. All right, so now coming to 2 big definitions right here. This is called the definition of a tangent line at a specific x value. So the notation is a bit weird. So notice that this little like apostrophe in calculus is called prime. So f of c without the prime is a y value. But when you put a prime on this, like a little apostrophe, and we call this f prime of c, okay, we're talking about the slope. That's what the prime means. It means slope. The slope of the graph f at c can be found by taking the limit of the difference of 2 y's and the difference of 2 x's. And if we were to subtract these 2 x's right here, these are the 2 x's. Remember on the first page when we subtracted these 2 x's, x2 minus x1, the c's canceled. So we're really just looking at delta x as the difference in the x values. So the definition of a tangent line at C, okay, and this is how it reads. The slope of graph f at C, or simply, not simplify, simply, f prime of C, f prime of C, f prime of C. And when we read f prime of C, we should be thinking slope. So it's the slope of f at C. And typically this will give us a specific numerical value. We'll know what the slope is if we know exactly what x value we want to find the slope of the graph at. Okay, let's compare and contrast these 2 definitions. Just kind of look at how they compare. Well, this right here is f prime of c, so this must be f prime of x. This is the slope of f at any x. Maybe I don't know what the x value is like I do over here. So where this c is, I'm going to replace it with an unknown x. It's still equal to the limit as delta x approaches 0. So these are the same, nothing's changed. But look up here in the numerator. Wherever we had c, if I knew what that value was, I have a c here and a c here. Well, now I'm going to replace those c's in this definition, okay, with an x. And the denominator is still the same as delta x. So look at what's similar, what's different. This typically will give you a straight up numerical value that represents the slope of the graph. This right here, when we use it, if I don't know what c is, or the specific x, this a lot of times will result in an equation, not a numerical answer. Sometimes it'll result in a numerical answer, but that's a special case when we have a linear function. Okay. Something else I want to point out here is this notation, f prime of x, has other variations. Okay. Instead of f prime of x, you might see y prime, because maybe instead of using f of x as our function that we want to find what we call a derivative, okay, or a slope to, okay, a lot of times we'll call that y equals f of x. So instead of f prime of x, we might call it y prime. Sometimes in our work, we're also going to find the rate of change of y with respect to x. It's a fraction, lowercase d's. This is read the rate of change of y, the y function, with respect to x, meaning it's usually y equals something with an x in it. So these are all alternate ways to call f prime of x. Another way is this operator called the derivative with respect to x of a function f of x. I would say the two most common notations are these two right here. All right, and then how do we read this? Like we read this over here. Let's do a recording of that. This reads the slope of the graph of f at any x, or simply we would just read it f prime of x. So these two formulas will allow us to find the slope of the graph. This will often be a number. This will often be an equation that we can then use to find the slope at a particular x. All right, so let's practice. All right, let's find the slope of the graph of a linear function. So it says find the slope of the graph of f of x equals 2x minus 3 when c equals negative 2. Just means that that's our x value. So what's the slope of this linear function? Well, if we have 2x minus 3, its y-intercept is down here at negative 3. It has a slope of 2. Our y-intercept is negative 3. Our slope is 2. So it really doesn't matter where you're standing, okay, on this linear function. If I choose the point right here, what's the slope of that line? Or excuse me, what's the slope of that graph at that point? Well, the slope anywhere is going to be positive 2 because that's what's going on here. So we're going to use some calculus to verify that the slope of this linear function anywhere is positive 2. We're going to do a lot of work. We're going to get 2. But it's good to see that these formulas do work to give us the slope of the graph when we already know the slope of the graph. So we're going to verify it using the definition of a tangent line at C, since I know the specific x value. So I'm going to use this formula, show you how to use it, and we should end up with an answer of 2, because no matter what point you're at on this graph, the slope is always 2. All right, so it says find the slope of this linear function when c is negative 2. So I'm just going to kind of do an illustration. Okay, here's negative 2. Let's go down and find the graph. I know the slope at this one point, okay, has to be the slope of 2. If you drew in the tangent line, what does that look like? Well, the tangent line is just going to lay on top of that actual line. Okay, so that's kind of a special case. All right, so if I'm asked to find the slope of the graph when c is negative 2, I'm going to come up here and access this formula. So notice it's f prime of c and then the equals, then the limit. There's no space between the limit and the difference of the two y values. Oops, let me close that. All right, so what's c? C is negative 2. So everywhere we see a c, we're going to replace it with negative 2. Right. the slope of f at x equals -2, or f prime of -2, is equal to the limit as delta x approaches 0. These 2 points are coming closer together. F of -2 plus delta x, close the parenthesis, minus f of -2 all over delta x. Well, if you try to evaluate this limit right now and plugged in 0 for the delta x's, not the x's, but the delta x's, you're going to get indeterminate. So we need to do more work. So let's come over here. I can get f of -2. I know what the function is. Go back to your original equation. Plug in -2 for this x, which means 2 times -2 minus 3. That looks like it's going to be -7. So that's what this ordered pair would be down here, -2, -7. So where f of -2 is, I'm going to replace it with -7 in my formula. So now I need something to replace in for what's in front of the subtraction sign in the numerator. I need to know what to plug in right here. So I'm going to come back over here and use my function again. And where x is, I'm going to replace it with -2 plus delta x. So in my original equation, here's an x, here's an x. Replace this x with the input x value. So also do the same thing for this x. That would be -2 plus delta x. Close parentheses, and then don't forget the -3. So all of this was our x originally. So now we can come back over here in the formula and insert things. So every time f prime of -2 equals, the limit's not gone away because I haven't plugged in the value of 0 for delta x yet. Okay, on the top, right here, I'm going to replace this notation with what it's equal to, and it's actually equal to, okay, this function. It's going to go up front. 2 times -2 plus delta x minus 3. Okay, and then I'm going to subtract, because I'm at the subtraction sign, f of -2. Well, f of -2 was -7. So I'll put that in here, all over delta x. Okay, if you tried to plug in 0 now for delta x, you're still going to get 0 over 0, indeterminate. So what do? Let's just do some algebraic work here. So bring down f prime of -2. It should come down every time. We never lose it. We want it to be part of our answer at the end. Okay, keep the limit statement. Okay, in the numerator, let's distribute the 2. So -4 plus 2 delta x plus minus 3 plus 4, all over delta x. Well, notice we can do some more cleanup, and what we end up with is 2 delta x over a delta x. So f prime of -2 equals limit delta x approaches 0, and I end up with 2 delta x over delta x, which is still indeterminate, but okay, think of these as variables. Those will divide out. They don't subtract, they divide out, so I'm just left with 2. So if I try and plug in 0, there is no remaining delta x, so my answer is just 2. So let me come up here. I wish I had another line to write down. So it's f prime of -2 equals, divide those out, no place to plug 0 in for delta x, final answer is 2. So we've done a lot of work. We've probably lost sight of what we were supposed to be doing, but what we were supposed to do is find the slope of this linear function at x equals or c equals -2. And we knew from our past experience with linear functions that this slope was going to be 2, and our answer ended up being down here exactly 2. So that's a lot of work to get a slope of 2 when we already knew it. However, how often are we going to be dealing with linear functions? Not often. Okay, most times we're going to be dealing with nonlinear functions, and we need this process to get down to a slope.